Hey everybody, welcome back to Pre-Calculus from our new remote learning system here. How this is going to work is I'm going to film some videos that basically give you notes on all of our new topics. You can look at this in a couple ways. You can either just watch the video, if that helps for you. You can print out this document, which was shared with you, and follow along and write along as I do. Or you could use a separate sheet of paper and take your notes there, whatever works for you. At this point, we're going to start moving forward to another coordinate system briefly, just to talk about what it is, and then we'll start using it for other things. So our learning target is to understand the difference between rectangular coordinates and polar coordinates. So in the past, most of the work you've done with coordinate systems, whenever you've graphed anything, has been what we call rectangular coordinates. We'll talk about why we call it rectangular in a second. Oftentimes you might see this also called Cartesian coordinates. This word Cartesian, it comes from a famous mathematician and philosopher named Descartes. You may have heard it or seen his name somewhere. In fact, Descartes was this guy right here. So this system, it's not, well, the rectangular coordinate system isn't always the easiest to work in. So we're going to begin to examine another way to represent points in a plane and develop a new system that we're calling the polar coordinate system. This polar, what I want you to think about is like the Earth. Say this is the sphere that is the Earth. The Earth has two poles. It has its North Pole, and it has its South Pole. So that's the type of polar we're looking at here. So in this system, points are going to be referenced as distances from and rotations around a pole. Slightly different than with a sphere like that. All right, so rectangular coordinate systems. You've worked with these before. So these are written as x, comma, y, which we know, where this x value is the horizontal distance and y is the vertical distance. From the origin. You've done this 100 times before, you're all familiar with it. X, again, is our horizontal distance, so to get to a point up here, maybe, x would be this horizontal distance. This would be x. That would give us our x-coordinate, and y is maybe right here. Y is our vertical distance. So these coordinates are x, comma, y, our vertical and a horizontal distance from the origin. However, when we look at polar coordinates, we're going to look at things a little bit differently. So these are written using a couple different variables. So written as r, comma, theta, where r is what we call the radial distance. So r is the radial distance, and theta is the angular distance. From technically a pole, but in our case, the pole that we're looking at is going to be the origin. So we'll say from the origin. All right, so what does this look like? Imagine if we're looking down at the Earth from above, essentially. We're going to start to form circles. So if I were to sketch a circle here, I want to make this a better circle, so I'll insert it. We have a circle centered at the origin. R is going to be the distance out. Say we have a point right here. R is basically this distance all the way out to that point. This is R. That's the radial distance. Whereas theta, or angle, is formed with the horizontal axis. We go counterclockwise. So it's the positive direction is counterclockwise. So oftentimes you'll see that written like this. Counterclockwise rotation is positive. CCW, counterclockwise. And that's what our polar coordinates will look like. So this point right here is written as r comma theta, where r is the radial distance and theta is the angular distance. And this point was nicely in the first quadrant there for us. So there's our difference between rectangular and polar coordinates. So let's take a look at how we can actually plot these down here. I want you to take a second and, if you want, pause the video and try to actually plot all of these on your own, and then once you've finished or gotten stuck or just want to check, you can play the video and see what I tell you. So take a second, pause it right here. All right, so this first one, plotting the point 3 pi over 4. The value 3, that's our radial distance, and pi over 4 is our angle. Key thing is, if we were to rewind back up here, this theta value, this can obviously be, because it's an angle measure, can be written in degrees, or we can use degrees or radians. I'll try to use both of them throughout this, that way we're familiar with what things look like with both, but they're just different ways of writing angle measures. So in our case, we have a distance of 3 radially from the origin, and angularly pi over 4 in, this is a radian measure. And again, positive rotations, that's counterclockwise. So for us, we should look for 3. Out, notice we have circles. We're going to go to the third circle out. So 1, 2, 3. And we're looking for pi over 4 is our angle. So this right here, this is our point 3 comma pi over 4. We don't need to put this drawing right there, but that's our point, 3 pi over 4. Same idea for the others, 5, 7 pi over 6. 7 pi over 6 is our angle. Count 5 out from the origin. 1, 2, 3, 4, 5. There is 5 comma 7 pi over 6. All right, in this one, we have a negative angle. So that's a negative rotation. So if a positive rotation went counterclockwise, then obviously a negative rotation is the opposite. It's clockwise. We've seen that with the unit circle. So pi over 6, the positive direction was right here, so it was that angle. The negative direction, same thing, just the opposite direction, should take us to 11 pi over 6. So this is equal to negative pi over 6 as well. And our radial distance was 1. Therefore, this point should be right here, 1 comma negative pi over 6. This next one was in degrees, but it's the same idea. This circle hasn't been broken up into degrees yet, so let's think about some things. We should know from the unit circle that pi over 4 was 45 degrees. That's a common one we've seen. Because we know that pi over 2 is 90 degrees. Pi over 6, well, this was 30 degrees. Pi over 3 was 60 degrees. So it's starting to seem like this whole circle has been broken up into equal increments of 15 degrees. 15, 30, 45, 60. Can keep going. This would be 75 degrees. Plus 15 would give us 90. Plus 90 would give us 105. Not plus 90, sorry. 90 plus 15 would give us 105. 105 plus 15 would give us 120 degrees. And plus 15 again would give us 135 degrees, which is what we were looking for here. Encourage you to take a second, just pause this video and go around and fill out the rest of the circle. But now that we have 135 degrees, we're looking for 4 as our radial distance out to 135. 4 is here. It says 4 comma 135 degrees. If you wanted in radians, you could have written 3 pi over 4 instead. For E, we have 3 comma 9 pi over 4. Fortunately, I don't see 9 pi over 4 here. However, if I were to keep going, this was 7 pi over 4. Hey, this happens to be the same thing as 2 pi, which we also know is 8 pi over 4. This is 7 pi over 4. 8 pi over 4 is next. Continue counting around. This should actually end up being 9 pi over 4. So we'll go 3 out as our radial distance, and hey, look, it's actually in the same spot as that very first point we plotted. It's a curious fact here. We have 2 points in the same exact place. It's something important to note that we ended up with 2 different coordinates that ended up in the same spot. G and E. G is 6 comma 97.5 degrees. 97.5, it's not on here, but hey, look, I know it has to be between 105 and 90. Actually, it's exactly halfway between there. So that's 97.5 degrees. And our radial distance was 6, so this point should actually be right here. 6 comma 97.5 degrees. Lastly, negative 3 comma pi over 4. What does it mean to have a negative radial distance? Well, we know that positive 3 pi over 4 was right here. It was essentially, do this in red, this distance. Took us from the origin out to there. We have the same angle though, so this time we're still rotating pi over 4, but we're going the opposite direction. So negative 3 should end up out here. So this is our point, -3 comma pi over 4. Has this same angle right here of pi over 4, but we just went the other direction from the origin. That's how we can plot polar coordinates when we actually know what the polar coordinates are. All right, a big thing is going to be our ability to convert to polar coordinates when we have rectangular coordinates. So let's consider this point P, which we're going to have at the ordered pair, the coordinates 3, 4, in our traditional rectangular coordinate system. We want to know, how could we go about writing this point using polar coordinates instead? I encourage you to just pause the video and see if you can do any of this right now. Follow these few steps. If you get stuck, start playing the video. If you finish, check your answer and see if you get the same thing as I do. So first thing, we want to plot this point 3, 4 on the coordinate plane. Horizontal distance 3, vertical distance 4. So the point should be pretty much right there. Hopefully I did that close enough. That's our point 3, 4. We'll call it P. Next, we want to draw a ray. A ray is basically just starting at a fixed point and going on forever in another direction, but draw a ray out to that point. We'll label the length of the ray R, which is our radial distance, and the angle formed by the ray, and the horizontal axis theta. We'll label this R and call our angle theta. All right. And notice, as always, we can use our favorite shape, right triangles. Right triangles are pretty awesome. We can use them for a lot of different things. They're fundamental towards finding distances and angles. So sketch a right triangle formed at this point. Simple enough. Use a couple different colors here. We'll call this side, this leg of it, that length of 3. That's our horizontal leg. And we'll have a vertical leg going up. I'll do that in green. And that length is obviously 4. Right, now it wants to know which trig function could you use right away to find the measure of the angle theta for this right triangle. We want to know what the heck is theta. Let's think back to our trig functions. Sine theta, its ratio is the opposite side divided by the hypotenuse. Cosine theta is equal to the adjacent side from that angle theta divided by the hypotenuse. And tangent theta is equal to the opposite side divided by the hypotenuse. So thinking of these and looking at what we have, which of these would be best? From theta, we know 4 and we know 3. We don't know this length R yet, so the hypotenuse isn't useful for us. What we know is the opposite side and the adjacent side. Since we don't know the hypotenuse, sine and cosine really aren't going to be much use for us right now because we don't know R, we don't know the hypotenuse. So we can say that tangent theta equals the opposite over the adjacent. I wrote that wrong down here. I'm sorry. It should have been opposite divided by the adjacent. Because we know the opposite and adjacent side lengths. All right, so we can set up the equation. Tangent theta equals, well, what was the length of the side opposite theta? 4. And adjacent is 3. And we want to solve for theta. Rewinding to when we've worked with solving trig equations, to undo a tangent function, we need to apply its inverse. Tangent inverse, or also known as arctangent, to both sides of the equation. The reason we do that is because tangent inverse and tangent are inverses. They undo each other. So that's how we isolate theta. So theta should equal the inverse tangent of 4/3. Well, we can use a calculator for that. You're all blessed with our favorite calculator, Desmos. Trig functions are all in the functions menu. We need the inverse tangent of 4/3. It defaults. The answer it's giving us right here is in radians. We can switch between the two, radians and degrees, by clicking on the tool menu and changing between them. I'm going to use degrees right now. So this should be approximately 53.1 degrees. I think that's what we got. 53.13 rounded to 53.1 degrees. So that's how we can find the angle theta. Well, how do you think we can figure out the distance r from the origin to the point? So looking at our triangle, we know two sides. We don't know one. We have this super awesome tool known as the Pythagorean theorem. So we can use the Pythagorean theorem. Comes up over and over and over again throughout math. So we can set up our equation. R squared is equal to 3 squared plus 4 squared. 3 squared plus 4 squared should give us r squared. And then we'll just solve for r. R squared equals 3 squared is 9, plus 4 squared is 16. 9 plus 16 is 25. Square root both sides. R should be equal to the square root of 25, which in this case simplifies. 25 is a perfect square to 5. So at this point, we have now found both r and theta. So our point, P, has a radial distance of 5. That was our r value. And an angular distance of theta, which equals 53.1 degrees. So in polar coordinates, the point P is at 5, 53.1 degrees. This tells us how far out to go from the origin, and this tells us the angle that we rotate, 53.1 degrees. Alright, I encourage you again to pause the video and try to do number 2, would be considering the point Q, which is at -3, 4. Starting us off here, -3, 4, we obviously know is located all the way up here in quadrant 2. Just like we did last time, we'll draw a ray from the origin out to that point, almost like a vector. And then we'll form a right triangle. The hypotenuse is that radial distance we're calling r. And this angle isn't going to be theta. In fact, theta is from 0, this is again 0 degrees or 0 radians, it's from 0 all the way out to our angle. So this is theta. That means, what the heck is this guy right here? Well, we don't know. It's something else. We'll just call it another variable. I'm going to use another Greek letter, alpha. So that's another unknown right now. We don't know what that angle is, but maybe we can find it. We know the side lengths of this triangle that we formed. This length horizontally is 3. I'm going to use positive lengths here instead of using negative. Yeah, it's in the negative direction, but let's consider it to be positive 3 right now. And vertically is 4. So at this point, I'm going to encourage you to think all distances should just be positive, unless specified otherwise. So again, we need to figure out what theta is. What is this angle? Well, we could probably figure out what alpha is. We know the opposite and the adjacent sides of alpha, so again, we can use tangent. This time of alpha is equal to the opposite, which was 4 over 3. If you notice, that's literally what we did up here when we solved for theta. So again, solving for theta, you would apply the inverse tangent of both sides. You'd have alpha equals tangent of 4/3, which we already saw was equal to 53.1 degrees. But we want to know theta, not alpha. So what is theta then? All right, coming in here then and looking at theta, it starts here and goes all the way over to this point. Alpha covered this much distance, but what we also know is that from here all the way around, well, how many degrees is that? It's half of a circle, which we know is 180 degrees. So to figure out theta, theta is 180 degrees, take away whatever alpha is. That should give us theta. So theta should equal 180 degrees. If you were using radians, this would be pi, minus what we had for alpha, 53.1 degrees. Quick subtraction, 180 minus 50 would give me 130, minus 3, 127, minus 0.1 is 126.9 degrees. You could use a calculator for that as well if you really wanted to. Therefore, now we have theta. Awesome. Now we just need to find that radial measure, r, the radial distance. So to find r again, we can use the Pythagorean theorem. R squared is equal to 3 squared plus 4 squared. Well, we just did that. R again would equal 5. Not always going to be that, but I just wanted to illustrate the difference between quadrants with basically the same numbers here. So either way, we see r is 5, therefore this point right here, r is 5. Theta here we found is 53.1 degrees. So our coordinates are 5, 53.1 degrees. All right, and one more here. We want to consider the point M. I didn't call that P on that other page, did I? No, I didn't. M, which is at 4, -5. So again, I encourage you, try to do this one on your own, and then follow along here to make sure you get the same thing. So 4, -5 is this point right here. We'll draw that ray out. And we can form a right triangle again with our horizontal axis. We'll call this length R. And again, this angle in here is not theta. Theta is the angle going counterclockwise, from 0 all the way around to here. That's our angle theta. So again, we'll call this little angle in here alpha, and we can label our side lengths. This is 4, and then here we went down 5. And we want to figure out what is alpha. Seems like we're ending up with this trend where we use tangent, because we know the opposite and the adjacent sides. So we'll use tangent theta to figure it out. Not theta, but alpha is what we can figure out with the triangle, tangent alpha. 5 is opposite of alpha, and 4 is adjacent to alpha. So we have this ratio, 5/4. Solving again, we can use the inverse tangent function on both sides of the equation. Isolating alpha, and we get tangent inverse of 5/4. Let's figure out what that is. So instead of 4/3, we had 5/4 this time. For fun right now, I'm going to use radians instead. In radians, tangent inverse of 5/4 is 0.896. This would be 0.896, 896 thousandths, approximately, in radians this time. But again, what we actually want to figure out is theta. So the question is, what is this entire angle all the way around to here? Well, since we're working with radians, we know that one full rotation is how many degrees? Not degrees, but how many radians? Well, 2 pi. So to figure out theta, we'll go 2 pi, take away this alpha, and that should get us back to theta. So theta is 2 pi minus alpha, which is 0.896 radians. Head back to the calculator. 2 pi, do it down here, 2 pi minus 0.896 gives us 5.387. So theta is equal to 5.387 radians. So we know theta now, cool. We want to figure out r. We can use the Pythagorean theorem to figure out r. Side lengths are 4 and 5. So r squared should just be equal to 4 squared plus 5 squared. Some quick math here. 4 squared is 16, 5 squared is 25. The sum of 16 and 25 is 41. Square root both sides, and r is equal to the square root of 41. 41 isn't a perfect square, and in fact it's a prime number, so we can't simplify this radical at all. We'll just leave it. So r is the square root of 41. So now we have theta and r. Theta is 5.387 radians, and r, we just found, is the square root of 41. So this point has coordinates. In polar coordinates, square root 41, comma, 5.387 radians. If you use degrees, that would work the same way, literally no different, just a different number. Right, and that's the first lesson from distance learning. You'll have some practice problems to work through. You can use all these notes to help you out through that. Have a great day, and I'll see you guys next time.